Assalamualaikum and good day to everyone. Today I am going to present about how electromagnetism is applied to our group project named Magnilift. So you guys must be familiar with the concept of magnetism, right? Magnetism is the force of attraction or repulsion between permanent magnets. Meanwhile, electromagnetism is the broader principle that links magnetism and electricity. Electromagnetism occurs when an electric current flows through a conductor, creating a magnetic field around it. This electromagnetic force is one of the four fundamental forces of nature and includes magnetic fields, electric fields, and even lights. When a conductor becomes electrically charged, it generates a circular magnetic field around the wire. This scientific principle is the foundation of an electromagnetic crane, a device that uses electric current to create a temporary magnet. By switching the current on and off, the crane is able to pick up and release materials efficiently. In this project, the electromagnetism is applied to design and build a simple electromagnetic crane to demonstrate how electricity can be converted into useful mechanical action.
Take a good, hard look at this image. This isn't a scene from a disaster movie. This incident takes place at Shah Alam, Malaysia in April of this year. A towering piece of machinery, a symbol of progress, suddenly becomes a chaos and danger. Not only that, cranes also cause noise pollution which disturbs people's harmony in that area. Of course, we don't want that to happen, right? That's why we create Magnilift, which can solve to that problem.
The core of our presentation revolves around three key objectives, which guide our entire research and construction process. So let's move on one by one. For our first and most hands-on objective is to build a working prototype of an electromagnetic crane. We utilize the basic and readily available components such as wires and switch to demonstrate the fundamental principle of electromagnetic. This step is crucial to understand the practical challenges to assembling and ensuring that all the components work together safely and efficiently. Moving on to the second objective, which is the core of our project. We didn't just want to build a crane, we wanted to understand its power. By systematically varying all the electric currents, which is by changing the number of batteries or the number of coils in our solenoid, we measured the resulting magnetic field strength and also specifically by how much weight the magnet could lift. The hypothesis we tested was the direct proportional relationship between input current and magnetic field strength and also the lift capacity. Finally, we move on to the evaluation of this project. We compared our electromagnetic system to a traditional and permanent magnet setup. Finally, we move on to application and evaluation. We compared our electromagnetic system to a traditional and permanent magnet setup. We also evaluated how our prototype could pick up and release the materials to prove its efficiency.
So next, I'm going to talk about the material that we are going to use in our project. So, our team has decided to use the copper wire, iron screw, gear, battery, motor, saw, scissors, thread, switch, and plywood. The function of the copper wire that we are going to use is we are going to create a coil, or better known as solenoid. When electric current flows through the coil wire, it generates a concentrated magnetic field, forming the electromagnet. Moving on, for the iron screw, it acts as the magnetic core, By wrapping the copper wire around a ferromagnetic material like iron, it can significantly concentrate and strengthen the magnetic field produced by the coil. For the gear, we are going to use it to transmit power from the motor. And motor, it is a device that converts the electrical energy from the battery into mechanical energy. And then we have a battery, the power source for the electromagnetic crane. After that, we have the saw and scissors that used to cut and shape the plywood or thread and copper wire. And we also have switch that used to open and close the circuit, which is very important because we are going to use this to control the electromagnetic force that we are going to use. And lastly, we have a plywood that is used as the base or the main structure component that mount the motor, gears, switch and electromagnetic setup. Now, let's move from the theory to the practical and see how these pieces are coming together to create a functional electromagnetic crane. First, we started with the structure. By using the plywood and tool, we built a stable frame with a horizontal arm. Next, we built the core of our project, which is the electromagnet. We tightly wrap the copper wire around the iron screw to create a dense coil or solenoid. This coil concentrated the magnetic field. Crucially, we made sure the wire ends were stripped of insulation for a proper electrical connection. Now, for the mechanics and the circuit, we connect the DC power source, aka battery, the electromagnetic coil, and the toggle switch in series to create our main circuit. Separately, we connected the motor and gears to the power source as well, forming a simplifying lifting system. Finally, we attach a string from the electromagnet to the motor's pulley system to control the lifting movement. Now, the final step is the test. Watch what happens when we flick the switch. When the circuit is closed, the current flows and the electromagnetic instantly turns on, allowing it to pick up the metallic object. The motor then lifts the load. This conversion of electricity into motion and control force key, which is lift. When the switch is open, the magnetic field collapses and the load is dropped. Our electromagnetic crane successfully demonstrates the principle of control magnetism, a force essential in everything from heavy industrial machinery to modern speakers.
In conclusion, this project successfully achieved its goal of creating a working two-motor crane prototype that demonstrates how a magnetic field can be generated and turned off simply by controlling the electrical current. Even with a plywood structure and a simple copper wire, the results clearly supported the basic principle of electromagnetism. We observed that as the electrical current increased, the magnetic field strength increased as well, allowing the crane to lift around 100 to 150 grams as expected. This design also proved that a clean and precise coil winding is enough to produce a strong and controllable magnetic field, even without using an iron core. One important finding was the very low residual magnetism when the power was switched off, showing that the magnetic force can be controlled instantly, fully on and fully off. Overall, this prototype works not only as a functional model, but also as an effective educational tool that connects electromagnetism theory to practical real-world application.